Gnanam Paramam Dheyam. Knowledge is supreme.
Good afternoon. In the last couple of lectures, we have been preparing for the basic concepts for the course, which I will be using throughout this course. And let me just summarize briefly. Last time I have introduced concepts of given a field K is a given field which I will call it a base field. Then we have defined what is a K algebra. Usually we use the standard notation for that is the capital alphabets A, B, C, etc. So let me use it A here. So it is a K vector space as well as a ring, and this vector space and ring structures are compatible with each other. And then in particular examples of the K algebra we will use are polynomial ring in one variable over a field and maybe more variables. Also a field extension L. L is a bigger field containing K, such that this K is a field of such a thing is called a field extension. So these are the examples of K algebra that we will use, and also we have defined the concept of K algebra homomorphisms. Also kernel of a homomorphism, image of a homomorphisms, all these you must have studied in the basic course on algebra and also linear algebra. And the most important thing I want to recall is what we have proved is structure of ideals, in the ring of integers, and also a polynomial ring in one variable over the field K. And we have proved that every ideal in these rings is principal. Principal means it is generated by one element, that is, it is generated by one element. That means, for example, in Z they are of the form multiples of a fixed natural number n, and in Kx it is multiples of the monic polynomial f monic. This is monic, means that leading coefficient is 1 and this n is a natural number, and then this natural number n and the monic generators are uniquely determined. This fact we will keep using and use again and again using, and because every ideal is of this form, these rings are usually called as we have already noted that they are integral domains, and because the ideals are principal, these rings are called principal ideal domains. And this is usually abbreviated as PID. And we have seen example that not every integral domain is a PID. For example, we have seen that the ideal in the polynomial ring over integers, in this ring the ideal generated by the notation is this 2 comma x. These are precisely zx linear combinations of 2 and x. This ideal is not principal. This I have left it as an exercise, but this is very easy to check that there is no polynomial, no single polynomial f, so that this ideal is generated by f. So this I will remind you to check in the exercises. Alright, with this I want to now define what is an algebraic elements or what is an algebraic extension. So definition, so this is algebraic elements. Okay, so let K be our base field. Many of these concepts can be done for arbitrary commutative ring K, but I am not going to do this. In this whole course, we are going to concentrate on the base field and then develop concepts with respect to this field K. But instead of a field extension, I am going to consider A to be K algebra, A to be arbitrary K algebra, arbitrary. I would also assume it is commutative K algebra. Actually, this also I don't want to assume, but to begin with, we assume. When the example comes, I will indicate that time. And we have an element, so x in small x in the algebra K algebra A, and I want to define when is x algebraic over K. I want to define this concept algebraic over K. This concept. So note that given any x in A, I have this evaluation map or substitution map. So substitution homomorphism. Defined by f, defined by x. This is usually denoted by epsilon x or Ex. So this is a map from the polynomial ring in n variable over K to algebra A. So what is it? Any polynomial f, I will map it to f evaluated at x. So wherever there is a capital X, I will substitute it small x, and note that the resulting element, this is an element in A because f has coefficients in K and A is a K algebra. So this is a combination, K linear combinations of the powers of x. And because it's an algebra, it's a ring, therefore powers of x are also there. So the substitution homomorphism is a map from Kx to A. And it is easy to say that this epsilon x is a K algebra homomorphism. What does that mean? That means whether if I have given two polynomials f and g in Kx, whether I add two polynomials first and then evaluate it at x, this result is same as f evaluated at x plus g evaluated at x. This is one. And if I multiply two polynomials and then evaluate at x, or if I evaluate the polynomials at x and then multiply them in A. This multiplication is in A, this addition is also in A. But remember, we are writing the same, but it is clear from the context that where the multiplication and additions are defined. This plus also we are assuming that 1 in this ring, 1 in Kx goes to 1 is same as 1, and if I epsilon x, that means I have to put wherever there is a capital X, I have to put small x, but there is no capital X in this, so this is same as 1, and this 1 is the 1 in the algebra A, 1A. So altogether this means that it is a K algebra homomorphism. In particular, it is a ring homomorphism. So in particular, epsilon x is a ring homomorphism, and epsilon x is a K vector space homomorphism, K vector space homomorphism together, and operations are obviously compatible. Now whenever you have a homomorphism between the rings, last time we talk about the kernel, and also we have seen, so epsilon x, the kernel of epsilon x, this is an ideal in polynomial ring in one variable over K. And we just now I told that last time we also have the structure of, we know all ideals in the polynomial ring Kx, all ideals are principal. So either the generator is 0 or non-zero. So we have two cases, kernel of x is 0 or kernel of x is non-zero, and in this case we know that kernel of x has a unique generator if we choose it to be a monic. So kernel of x is generated by a monic polynomial mu x, where mu x is a polynomial in Kx such that it is monic. This is what we know from the last lecture, that all ideals are like this. Now we will analyze further, but just before I go on, I just make a definition here. An element x in A is called algebraic over K if kernel of epsilon x is non-zero. So that simply means that is there exists a polynomial mu x non-zero in kernel of x, and remember a polynomial in kernel of x if, so that is mu x is in the kernel means, mu x is a polynomial in the kernel means, mu x is a polynomial in one variable and it is in the kernel means whenever I substitute capital X equal to small x, it is 0, means mu x evaluated at x is 0. But this, in other words, this x is a 0 of the monic polynomial mu x in Kx. and mu x is non-zero. Then we call such an element to be algebraic over K. Now, there are several observations I want to make about this mu x first, and then we will go on. So, first of all, we should see some examples that where an element is algebraic and where the element is not algebraic. So, before I go on, if x is not algebraic, then we say that x is transcendental over K. Over K. This is same as saying not algebraic over K. And then first we want to see some examples. One, for example, now my base field is Q, and the algebra I take is, for example, R. This is field extension. So, think of R as a Q algebra. So, and look at the element x in R, which is say root 2. Everybody knows that root 2 is a real number. There is a root 2, there is a square root of 2 is a real number, and which is not a rational number. So, this is not rational. This is in fact a very easy consequence of the fundamental theorem of arithmetic. Okay, so, and what is the map? The map we are considering is evaluation or substitution map at root 2. So, this is a map from Q polynomial x to R. The map is any polynomial f. You take f and substitute f equal to root 2, x equal to root 2. So, f of root 2. So, for example, where will x go? X goes to root 2. Where will x plus 1 go? This will go to root 2 plus 1. So, where will x square minus 2 go? This will go to root 2 square minus 2, which is 2 minus 2, which is 0. So, here is a polynomial which is non-zero and it goes to 0. So, that means this polynomial does belong to the kernel of epsilon root 2. This is precisely what we have defined, that therefore, root 2 is algebraic over Q. We just have to test whether this substitution homomorphism has a non-zero kernel, and there is nothing special about root 2. So, here also I want to clear one confusion, or one not confusion, but writing style which one should improve, that is, I am not going to write root 2. So, 8. So, instead of writing root 2, this is because it is ambiguous whether you are taking a positive sign or negative sign, and when one writes this, one will have always thing in mind whether you are taking positive sign or negative sign. In order to create to be more precise with this, instead of this I am going to write small x in R such that x square equal to 2, small x square equal to 2. And how many possibilities are there? We saw, that means, this means that is x is a 0 of the polynomial capital X square minus 2. And we know if x is a 0, then minus x is also 0. Of the same polynomial, because when you square it, whether you take minus x or small x, it is same. So therefore, our standard writing will be x such that x square equal to 2. So there is no question of, we are not talking about sign or anything here, and it's no and nothing special about root 2. We could have taken any polynomial of this type, x power n minus say 2, or why that, x power n minus any rational number q is any rational number. So that means what? We are looking at the zeros of this polynomial, and we have noted that this polynomial has at most n zeros. And now you would have seen in the definition of real numbers that when do you definitely know that such a polynomial has a 0 or real numbers? That is when n is odd. When n is odd, x power n minus q always have 0 in R. This is precisely what you prove in your college days, the so called intermediate value theorem. Intermediate value theorem. So in other words, given a rational number q, it always have a nth root as a real number. The roots are not rational numbers in general, but if n is odd, then definitely there is a real number who is a 0 of this, and those real numbers are called nth roots of q. And one can also give a criterion when the rational number has a rational nth root. That will only when that will depend on the prime decomposition of q. I will not go there into that, but it is possible by looking at that is much easier. If I know prime decomposition of q, and if all exponents of the primes which occur in the prime decomposition of q are divisible by n, then this also has a nth root in q already. For example, 4 prime decomposition is 2 square. So when I take a 0 of x4 minus 2, x4 minus 4, x square minus 4, that has a square root, a rational number, that is namely 2 or minus 2. These are the square roots of this. So that is much easier criterion to say that when such a polynomial has a rational 0. So also when n is odd, one can assert that this polynomial has a real zeros, and all these zeros are by definition therefore algebraic over Q. So more generally, if I have a polynomial f over any field k, Ax, and if I have a bigger field L, and there if x is in L with f of x is 0, if such a x exists, then that x is algebraic over K. Then x is algebraic over K, and of course f is non-zero. So that is because you see all that you need to check, that is if I take this substitution homomorphism from Kx to L, epsilon x, where do capital F go? Capital F is given to be non-zero and it goes to f of x, but f of x is 0. That is how x is chosen. That means kernel of epsilon x is non-zero. In fact, f belongs there, and therefore we say that x is algebraic over K. So you see, the zeros are very closely connected to algebraic elements. So this was the field case, but I want to also show you it's natural to consider an example where L is not a field. For example, this example is, now I want to remind you that I am not assuming that the algebra I am considering in this example is commutative. So this example, give it 3. So K is any field, and A is the algebra I am taking M2K, let us say. M2K is algebra. This is 2 by 2 matrices with entries in K over K, and we know how to add two matrices, how to multiply two matrices, how do I multiply scalar with a matrix. So with those operations we know this M2K is a K algebra, and it is definitely non-commutative. And now I take arbitrary matrix. So A, B, C, D. This is a 2 by 2 matrix with entries in K. And I want to now show you that this element is algebraic over K. So this is my X. To show that X is algebraic over K, I have to consider this substitution homomorphism capital X AX to M2K, which any polynomial f is mapped to f of, you substitute instead of x this matrix A, B, C, D. And what do you need to check? We need to check that there is at least, this is the substitution homomorphism by x, this is our x now. We need to check that kernel of epsilon x is non-zero. Well, the right candidate for that, one might have guessed, that is, you look at the characteristic polynomial of this x. So characteristic polynomial of x over k. In this case, we know it is a monic polynomial of degree 2. So the characteristic polynomial of this 2 by 2 matrix is usually denoted by a characteristic polynomial, and that, let me denote A as a matrix. A is this matrix. Then this is by definition the determinant of x minus A, x minus D, minus B, minus C. This is whatever polynomial, it is a polynomial of degree 2, monic. So it is x square plus px plus q, and your famous Cayley-Hamilton theorem says that if I substitute instead of x the matrix, the original matrix I started with, then I get it 0. That means chi of A evaluated at A, this is actually 0 matrix. That precisely means, so in other words, this chi of A is a polynomial inside the kernel. Remember, x I have called it A. So therefore this is a non-zero polynomial because its monic and degree is 2, and therefore what we conclude from here is this matrix A is algebraic over K. And there is nothing special about 2. So more generally, what we note, the same proof tells you that if I take A to be Mn K, n cross n matrices over K, and I take a fixed matrix A, and I take the evaluation or substitution homomorphism defined by this A, that is a map from Kx to Mnk, then this kernel of this epsilon A definitely contains the characteristic polynomial of A, which is a non-zero polynomial monic of degree n. So that simply means in our language that is A is algebraic over K. So all matrices are algebraic over K, and this is very important. In fact, linear algebra, as you have noticed, is centers around studying the characteristic polynomial, zeros of the characteristic polynomials, and therefore we have lots of ready examples to go on. And with this definition, I will next couple of minutes, I will deduce how do you check. This is only a definition and we know examples, and also I will give examples which are not algebraic, and we will also study how do we see the elements are algebraic or not. How do you find a economical criterion for elements to be algebraic or not. So this I will continue after the break. Thank you.